welcome to this lecture on modeling, analysis and estimation of three-phase unbalanced power network. In the last lecture, we have talked about the twisting of a conductor or rather twisting of a transmission line, and also we have looked into one concrete example. We have also looked into a numerical example. In this lecture and from this lecture, we will talk about the calculation of impedance of a transmission line involving bundle conductor. So, we talk about calculation of so for that we let us consider a case and then let us consider a case that I have got a 4 conductor line. I have got a 4 conductor line X, X dash, A dash, B dash, C dash, and then I do have ground also, local ground. This we have already, and then this is the remote ground. So, this is the local ground, this is the remote ground. We have already seen all this. So, and then we know that the effect of this ground can be represented by a fictitious conductor at some length dd dash, and this is also connected to ground, fictitious. So, this point is always grounded, and then this is also the fictitious conductor, this is also connected, this is also connected, this is also connected, this is also connected. So, this is the case. So, I have got essentially 4 original conductors and 1 fictitious conductor dd dash, and this fictitious conductor dd dash takes into account the effect of the ground. So, we know that, and we, so then of course, we have got the current Ix, Ia, Ib, Ic, and then we have got the current Id, and we have already seen. So, then by current relation Ia plus Ib plus Ic plus Ix is equal to minus It. So, this relation also we have already seen. So, this also we know, and or in other words we can write it down that Id is equal to minus this, we can certainly do. And then for these 5 conductors, if I write down the voltage equations, I can write it down as Va minus Va dash, Vb minus Vb dash, Vc minus Vc dash, Vx minus Vx dash, and then Vd minus Vd dash. That would be is equal to ZA These are the primitive impedances: ZAB, ZAC, ZAX, ZAD, then ZBA, ZBV, ZBC, ZBX, ZBD, ZCA, CP, ZCC, CD, then ZXA, ZXP, ZXC, ZXX, ZXT, ZDA. And these are, put a over bar on them to denote that these are primitive impedances. And of course, we also note that these are also, all of them are complex quantities. So, what are the expressions? We know that ZPP is equal to given by Rp plus J omega k log 2s by dsp minus 1. That we have already seen. This is omega per unit length, where P takes the values D, right. So, ZA, ZBB, ZCC, ZXX and ZDD are given by this expression, and ZPQ is given by RD, which is actually is J omega k into log 2s by d pq minus 1. It is also omega per unit length where P is equal to a P and Q both. So, I must write P and Q both with the condition that P is not equal to Q. So, this is the case. So, now from these two equations I can write down. Now, here of course, I know that Vd is equal to 0. I must also note that Vd is equal to 0 and Va dash minus Vd dash is equal to 0. That we know, and also basically Va dash, Vb dash, Vc dash, Vx dash as well as Vd dash because they are all connected to the same point, so then therefore these quantities are all equal to each other. And now we, by the same method, I just do this, that VA minus VA dash. So by subtracting, let's say subtracting row 5 from row 1, we get, so by subtracting row 5 from row 1, we get that VA minus VA dash minus VD minus VD dash is equal to ZA minus ZDA. So it is ZA minus ZDA IA plus ZAB minus ZDB into IB plus ZSC minus ZDC into IC plus ZAX minus ZDX into IX plus ZAD into ID. Right. So now I replace ID is equal to, now I replace ID is equal to, and we also note that ID is equal to minus IA plus IB plus IC plus IX, that I note, so that I replace. So if I do that, and I know that VD is 0, and so then therefore it will turn out to be VA is equal to, because it is basically would be VA minus VD minus VA dash minus VD dash. So this would be the case, right? So it would be equal to this, and of course this particular VD dash is 0, and of course VA dash minus VD dash is also 0. So then therefore only VA will remain. So then VA would be is equal to ZA minus ZDA, and then ZAD plus ZDD into IA plus ZAB minus ZDB minus ZAD plus ZDD to IB, then ZAC minus ZDC minus ZAD plus ZDD into IC. By the way, these are all primitive values. So these are also all primitive values. Plus ZAX minus ZDX ZAD right? So we can do these similar operations for VB, VC and Vx, and if I do this similar operation, and for example, and of course we then denote this quantity as, let us say, ZAA. I denote this quantity as ZAA. I denote this quantity as ZAB. I denote this quantity as ZAC, and I denote this quantity as ZAX. Please note, now these quantities are all without any overbar. So all these impedances are now without any overbar, and these impedances are expressible in terms of the primitive impedances. Now if I do this same operation, that is, now if I let us say I subtract rho 5 from rho 2, I will get similar equation for VB, and then if I do subtract rho 5 from rho 3, from rho 1, it is rho 1, from rho 1 we get, so it is rho 1. So then if I now subtract rho 5 from rho 2, I will get equation for VB. If I subtract rho 5 from rho 3, I will get equation for VC, and if I subtract rho 5 from rho 4, I will get equation of Vx. And we will get similar equations, and if I do now collect all these equations for VA, VB, VC and Vx, and then do write down in the matrix form, I will get same equation VA, VB, VC, Vx is equal to ZA, ZAB, ZAC, then ZAX, ZBA, ZBB, ZVC, ZBX, right. So I just, for the sake of completion, just we say that VB I get from rho 5 minus rho 2, this I get from rho 5 minus rho 3, and this I get rho 5 minus rho 4. And the expressions, the general expressions would be essentially that ZPQ is equal to ZPQ minus ZPD minus ZDQ plus ZDD. It is where, and P and Q varies from A, B, C, X. So this is the general expression. So for example, we can do a test. For example, if I set P is equal to A and as well as, let us say, Q is equal to A, so then therefore I will get Z bar A minus Z bar P D. So that means basically z bar AD. So I have got z bar AD. Then I have got minus z bar dA, z bar dA plus z dd. If I set, let us say, p is equal to a and let us say q is equal to c, so I will get z bar AC, z bar AC minus z bar AD, so z bar AD minus z bar DC minus z bar DC plus z dd. So then similarly all the other expressions are also expressions. So this is the general expression. So this is the general expression. Right. So this is the general expression. Now we are considering actually the bundle conductor. So then if I consider a bundle conductor, so this is the case for when all these four conductors A, B, C and X, they are separate. Now suppose I consider a case a bundle conductor case, so then where the case is something like this. So now let us take the case a bundle conductor case. So let us say so this is x dash a and actually conductor x and a, they are joined together. So essentially, and these composite conductor consisting of two conductors in parallel, or rather I say that these composite conductor consisting of two conductors in bundle, that is consisting of phase A. So this is now composite phase A, where this phase A is now consisting of the conductor x and A. So if that is the case, so now if I apply this, and then of course after that this configuration is same. So I have got local ground, remote ground, and then this dd dash, and then this is, so this is now the essentially the case of right. So this is now the essentially case. So now this is a case of bundle conductor. So now I can say that this is my say phase A, say phase, this is my phase A, this is my phase B, this is my phase. So where phase A is consisting of a bundle conductor. Now because conductor X and A, they are in parallel, so then therefore I can write down that Vx is equal to Va, or in other words Vx minus Va is equal to 0. So now if I use this, so then therefore now from this relation, I can write down, now from here I can write down, okay, so from here I can write down that Va is equal to Zaa into Ia plus Zab Ib Zac Ic plus Zax into Ix, and then Vb So, these are the equations. So, I can say that these are equation say 1, 2, 3 and let us say 4. So, then therefore, now if I do implement this equation, so then therefore, so from equation 1 and 4 I can write down that 0 is equal to ZAA minus ZXA into IA, or rather I can also say that ZXA minus ZA is equal to IA. So, let us write down in that fashion. So, it is ZXA because it is Vx minus Va. So, ZXA, so ZXA minus ZA into IA plus ZXB minus ZAB into IB plus ZXC minus ZAC into IC plus ZXX minus ZAX into IX. So, this I call equation 5. Now, if I write down equation 1, 2, 3 and 5 together, writing down equation, so equation 1, 2, 3 and 5 together, writing equation 1, 2, 3, 5 together in matrix form. What we get? We get that VA, we get VA, VB, VC, last term is 0 is equal to ZAA, ZBA, ZCA, this is ZXA say minus ZAA, this is ZAB, ZBB, ZCB, and then this is XB minus ZAB, XB minus ZAB, then ZAC, ZBC, ZCC, ZXC minus ZAC, then ZAX, BX, ZCX, ZXX minus IA. Now, so from this equation I can write down that VA is equal to ZAA IA plus ZAB IB plus IX. Now that I can write down as ZAA into IA plus IX, because you see now because of this bundle conductor, total current in phase A is phase capital A is IA plus IX. So, here the current would be IA plus IX, here the current is IB, here the current is IC. So, to simulate the case of phase A bundle configuration, we have to take the current as IA plus IX plus ZAB into IB plus ZAC into IC plus ZAX minus ZAA into IX. So, similarly VB, so that I can write down. Similarly VB, I can write down that ZBA into IA ZBB to IB so I can write down it as that ZBA into IA plus IX plus ZBB into IB minus ZBA to IX, and VC is equal to ZCA and the last row remains the same. So, I stop here, and we have to also modify the last equation, which we will do in the next class. Thank you.